So
Okay.
welcome everyone, and I'm happy to give this talk. I'm in my home in Portola Valley, California, which is right outside of Stanford. It's in California, so it's earlier than I usually get up, but I did have some coffee, so hopefully I will get through this. So today, I mean, this talk is not really, I would call a hardcore research talk. Most of my work is in computer graphics, and over the last few years, I've been becoming more interested in building hardware. And I actually gave some talks at programming language conferences about that. I actually gave a keynote at ICFP a couple years ago. And so I've been learning a lot about different ways of abstracting hardware. And I've come at it from a software background. So I wanted to just tell you about some things I discovered and know about. Some of you probably know about these things, but I thought they were pretty cool. So my talk is really just, some cool things I've discovered about hardware. So the first thing I have to do is, motivate hardware design a little bit. I know everybody here is probably a software person. I do think there's a tremendous opportunity for people in programming languages and software to get involved with hardware. And, it's actually a very interesting time in hardware right now. So many of you have seen these, predictions that Moore's law, which it might end. Okay, so here's a graph of Moore's law, and you see that we've had this incredible increase in the number of transistors going back all the way to like 1970. And here, this cuts off in 2016. And you're sort of right on the edge of people being able to build smaller transistors. I mean, you may have seen there's been some chips designed by Apple in particular that were at 5 nanometers, but we're right at the edge where we're getting down to sort of the molecular level. And the other big issue that's come up in hardware, besides the end of Moore's law, is there's this other more technical thing called Dennard scaling. So it turns out, and I'm not going to go through this in great detail, but this is sort of some what are called scaling arguments, which sort of show that if you make a transistor smaller by some factor X, okay, so if the length of that side of a decreases by some factor X, say by a half, okay, then the area, of course, goes as X squared or 1/4. And then there's all these other electrical properties like resistance and voltage and capacitance and energy and time and so on. And there's this interesting thing called capability, which is the area times the time at which you can switch the transistors. So in some sense, that's the amount of compute power you have, right? Because the bigger your area is, the more transistors you have, and the faster you switch, the more calculations you can do per second. Okay, and if you divide the power used by the chip, which is the energy divided by this capability, Dennard's law said that was 1, which is sort of an amazing fact. And what that meant was, as we made more and more powerful chips, they consumed roughly the same amount of power. They were ISO power. But this is no longer true. And so what's happening now is, for various reasons, mostly having to do with the voltage that we can drive these things at, we cannot run at ISO power. So if we make bigger chips, they consume more energy and basically get hotter. So you might think this would be the dark age of computing. I mean, that we're finally sort of, the free lunch is over, right? There's no more Moore's law. We can't build chips that are more powerful. And this has been a topic of quite a bit of discussion in the computing industry. It could completely change our field. Maybe my grandfather used to be a mechanic, and when he grew up, he became a car mechanic. And that was a very high-tech industry at the time. This was in the early part of last century. And then, of course, cars became, much more standardized and wasn't nearly as exciting. You couldn't get a PhD in mechanical engineering to build cars. So, but, there are people that think this is actually the most exciting times in hardware. So my colleague at Stanford, John Hennessy, actually won the Turing Award a couple years ago. And he's talked with Dave Patterson, was called a new golden age for computer architecture. And what they observed, and a lot of other people have observed, is you can build lots of different kinds of computing devices. So this is a sort of a chart by Bob Broderson, where all we have here is different processor designs. So these are just various like designs that people have made for different kinds of computing elements. And you see, and then what we have is energy here, energy efficiency actually, which is how much energy does it take to do a particular operation. And you see there's this incredible range in sort of efficiency. Microprocessors tend to be very inefficient. And then there's this dedicated hardware, which can be literally 10,000. Remember, this is a log scale. These things can be 10,000 times more efficient. A factor of 10,000 is pretty significant. And so the argument that John and Dave made was that the reason we're going to enter a golden age is we're not going to be sort of stuck building these conventional microprocessors, which we've been riding along with, but we can build much more interesting hardware. And yeah, I've done a lot of work with GPUs that might sit in here. Okay, there are DSPs of various types and so on, and custom ASICs, for example, if you run a video codec or something, it's probably an ASIC. And so there's tremendous room for making hardware more efficient. But the way you do this, in some sense, I mean, these processors are sort of general purpose. They're all the things we love. But as we make things more specific, we have to make them more domain specific, right? And so instead of just having one or two types of processors, like an ARM processor and x86 processor, we might start having hundreds or thousands of different kinds of processors, all specialized for tasks. I sort of like this idea. It reminds me a little bit more of biology, right? I mean, I know sometimes we have very simple ecosystems with only a few creatures, but oftentimes we have very diverse ecosystems with lots of different creatures. And so, so this is actually quite exciting. And you're starting to see this in industry, in particular in the machine learning area, where people do tensor processing very, very efficiently. And many of the biggest advances in machine learning and artificial intelligence, like the work by DeepMind on AlphaGo and so on, are fueled by this much more efficient compute substrate. So that's how I sort of got interested in this subject. I've dabbled in hardware, I've dabbled in architecture, but it just seemed like, this could be really interesting. So what I want to talk about today is, like, I'm a software person. So how should we think about hardware? And some of this is, I'm sure but I just want to, go over some of these basic hardware abstractions, because it's not that complicated. But I know a lot of people, it used to be that everybody learned a little bit about hardware when they learned computer science. Nowadays, you can easily go through computer science without learning anything about hardware, which is, I think, a bit sad. So the first thing about hardware, right, is we build these little circuits. So here's a circuit I made in a program called LogiSim, which some of you may know about. It's a fun little program for educational purposes to help you model circuits. This is what's called a full adder, right? These are AND gates. These are OR gates. And these are exclusive OR gates. And what this thing does is it actually computes the sum of 3 bits. So, 1 plus 1 plus 1, which could equal 3. And so there's 2 bits that come out. One is the sum, right? So if you have 1 plus 0, you get 1. And then you might get a carry. So you get 3 bits in and 2 bits out. And so you can implement this with this little circuit. And of course, everybody knows about logic and so on. And, we build computers out of these simple gates. So this is an example of what's called combinational logic. So combinational logic is a fixed size. In other words, in that example, there were a finite number of gates. They're arranged in some kind of, think of it like an expression tree. There are no cycles in this, right? I mean, you have a what we might say was we have a pure and total function of the inputs, right? I mean, if you have valid bits coming in, right, all your inputs are valid. And of course, it's defined for all possible input values, and it's purely functional. There's no state there. All these are all compute elements. And this circuit is sort of interesting. It's continuously computing, right? If you change one of those bits, it takes a little while for the information to propagate through the circuit, but so there's a certain delay in that. But it continuously computes, and it computes in parallel, right? So each of those gates is computing all the time. I'm just emphasizing these factors because it's a little bit different than how we think of programs, right? We don't think of programs as all the expressions are continually computing, right? And we don't think of all the expressions as being in parallel, right? We tend to think of it very sequentially, but that's what's different about hardware. Hardware is fundamentally parallel. So, hardware design, if you think of these combinational circuits, hardware design is a natural for functional programming. And of course, there's been a lot of work. Mary Sheeran, I'm sure many of you know, has worked on this for many years and built a lot of very inspiring systems. Some of these are in Haskell, like Lava and so on. And so, actually, when I gave the ICFP keynote a couple years ago, I was actually looking at the history of the conference, and the original title was actually called Functional Programming and Computer Architecture. I mean, people actually thought, I think in the early days, that maybe one of the prime applications of functional programming might be hardware and architecture. So there's one more thing about hardware I have to tell you about, is that we have state in hardware, right? We have memories of some type, which always is a bit of a problem for functional programming. I mean, I'm not going to start, you might think, oh no, we're going to start talking about monads or something like that. But let me just describe how that works, right? We have these things called flip-flops, or sort of memory cells, and they have some input and some output. And what happens is, normally what we do is we have a clock, and whenever the clock edge rises, goes from 0 to 1, we say we latch the value of D into the flip-flop, and it's stored there, and it continues to be output on Q until we get another rising clock, in which case we could change the value. So the idea is that we have this little state element, this 1-bit thing. Of course, we can organize this into registers and more complicated things, but the primitive is this flip-flop, and then it's clocked, right? So we do have this notion of time, and we have this notion of state. So that leads to the main other case, this is really pretty much the main conceptual things in hardware, is we have this idea of sequential logic. Now, we wouldn't need to design hardware with sequential logic, but everybody does, okay? So the new output value is a combinational function of the inputs, and the value is currently stored in the D flip-flop. So this leads to what we would call a finite state machine. And so we have this state, okay? We have this combinational function of the state and the inputs that gets sent to the inputs to the state registers, the flip-flops. And then when the clock rises, all the flip-flops change state. So normally we have a global synchronous clock. So this is fairly interesting. It's very different than like a distributed system. Although people are starting to build distributed systems with global clocks nowadays. I mean, it's sort of an interesting, it's a slight, when we learn about parallel programming models, we don't typically learn about this one. In a typical parallel programming course, we learn about, CSP or various other things. Now, we can, in modern circuits, we might not have a global clock. It's very hard to have a global clock on a big chip. There might be what are called clock domains, and then you have to communicate across these clock domains. I mean, there's a lot more complexity here, which is very interesting, but that's the basic idea. And so we get these finite state machines, right? Where we have these inputs. So there's two kinds, a million more. I'm not going to go into this. We have some state, we have some combinational logic, and so on. And then that's what a computer does. So a computer, is a finite state machine. I mean, in parallel, it's running this finite state machine. It's not a Turing machine. It's a finite state machine. So, so most computers are organized like this. So this is just sort of a summary of that. So what we actually have is sort of an interesting thing. I'm going to call it, we're going to have a reactive time varying spatial program. right? It's a spatial program, and these circuits are laid down on the chip, and they're continuously computing, and they're laid out spatially. But then it's time varying in that we have this sequence of state updates due to the finite state machine. And I'm not going to talk about it today, but if you design hardware, you have a hardware design language, which is a program that generates the hardware itself. The hardware itself is this finite state machine. So you have a design program that generates the finite state machine. So, you know, when my work more recently, I've been working a lot on stage metaprogramming as a way of designing hardware design languages. But I'm not going to talk about that. Okay, so one question is, so how could we implement this state update with a functional program? And this has led to a notion, which again, I know most of you know about, called reactive programming or streams. So I just want everybody to understand this because it's sort of an old idea, but people have a lot of ideas sort of get lost. And so I want to just remind people of it. And if you're maybe younger, you might not know about it. So here's the idea of a stream. So, and this is some Haskell. So the idea of a stream is really, just imagine you have sort of a infinite list of values of some type. And so you can think of this list as having an index, right? It starts at 0, then there's a first element, a second element, a third element, a fourth element. It could go on infinitely. So what you can think of this stream is a mapping from some discrete time, t equals 0, t equals 1, t equals 2. Remember, we're going to start at 0 here, so you might call it a semi-infinite stream, to some value. Right, so in this list are stored different values. So sort of that stream sort of captures the evolution of the state, right? So if you think of one of these flip-flops, right, every time the clock ticks, you add an element to this stream. So it comes up in some initial state, some reset state, then you start computing, you update its state, then you update its state, and you update its state, and you create this stream. And then there's sort of two fundamental things, which one is our very familiar map, which just maps a function over a list. So this function is sort of equivalent to the combinational logic. So it's not an arbitrary function, it's some expression of the value in the list. Okay, so I just wrote out one, it's called invert, which, if we were to write this out in Haskell, you just say map the function not, right? That just turns false into true and true into false. Okay, and so now we have this this function that could be running continuously over this list as it changes values. And then, we're gonna say our register has some initial state, init, and then it has some other stream. So it has an initial value A, and then there's a stream. And so init just says, I'm going to take a stream, and the first value in the stream is going to be the initial value, and then it's going to be defined from then on. So we have to come up in some predefined state. But once we enter that predefined state, we can compute new elements in the stream. So here's a program. Actually, let me just, I'm going to run this program. Let me just fiddle with this. I have to get my keyboard out here. Okay, I hope you can see two windows. Probably shouldn't be giving a demo here, but I'm going to try. Okay, so here's this program. So this is a Haskell program. I have my stream. I define this invert function. I define this register function. And then I'm going to make what's called a toggle flip-flop, which is a little different than a D flip-flop. And a toggle flip-flop is just going to be alternating between 0 and 1, or false and true. So what we're going to say, and this is our equation for that. Actually, let me. So this toggle flip-flop is actually given by this circuit here. So we have a D flip-flop here. That's what this box is. And the output is Q. And then usually flip-flops have Q and not Q as outputs. So this is not Q. So if Q is 1, not Q is 0. And we just feed in not Q back to the input. And we have this clock over here. So this is just going to be a circuit that alternates between 0 and 1. It starts out, or false and true. It starts out in false state. That's what this register says. Okay. So we say Q equals the register which starts in false, followed by some stream. And stream is defined to be the inverse of Q, the not of Q. Okay, so this is actually a fairly interesting program. I mean, first of all, it runs on infinite streams. It runs forever. Q is an infinite stream. And notice it's mutually recursive, right? Q is on the left-hand side here, is on the right-hand side here, and D is on the left-hand side here and the right-hand side here. So this is actually sort of interesting program. I mean, you know, it's, and this recursion is due to this cycle in the computation, right? There's a cycle in the computation. So if you have a cycle in a computation, you're going to get this kind of mutual recursion, right? Because the input is fed back, or the output is fed back into the input. So, you know, this program runs in Haskell. In fact, I can run it for you. So let me. Okay, so this is an infinite stream. So I'm going to run this operator take. I'm going to take the 4 elements from that stream. So T flip-flop is a stream. I take 4 elements. I get false, true, false, true. If I change that to 100, I get, you know, a long stream, and I could just keep computing this as long as I wanted. So this is a, you know, here's the value at time t equals 0, t equals 1, t equals 2, and so on. So this is actually a pretty neat program. I mean, you know, I mean, there are not a lot of languages you can write this program. And it depends on the fact that, you know, Haskell uses lazy evaluation, and you can define things recursively this way. And that the list structures in Haskell are implemented so this works, okay? So it's actually a pretty, I mean, it's a really simple program, but I think it's a pretty cool program, actually. So that's the idea of a stream. So the tricky part is this recursion here, this sort of the cycles in the graph, and the fact that it's you know, infinite stream. It's not finite. So you know, this is sort of, so I really think this is cool. So what, you know, I mean, there's no, well, I guess you could argue like the list is a monad or something like that. But, you know, we just take this familiar thing called a stream, right, or a list, okay, and now we've been able to write sort of a hardware simulator, okay. We have the notion of combinational logic and sequential logic, okay, and of course, when we run this program in hardware, it is a little different. I mean, in software, we run the thing sequentially. Every instruction is done at a different time. In hardware, the circuit itself, right, the body of the where clause, is actually laid out in hardware and runs in parallel in sort of lockstep. And of course, we use this finite, we convert it into a finite state machine. So we'd have to compile that to hardware, we'd have to convert the mutually recursive graph of equations, right, into a finite state machine, where we'd have to separate out the registers from the combinational logic. And it's sort of interesting to just keep repeating this, but, you know, hardware is sort of this spatial temporal thing, or space-time computing thing, where we have things running sort of in parallel in space on the chip itself, but then, you know, sequentially in time. So a lot of the properties of hardware that we think of as programming languages are due to the sequential operations in time. But sort of what makes hardware efficient is the fact that a lot of it is mapped into space. Because the part that's mapped into space is running concurrently, and you know, it can be sort of arbitrarily parallel. And so, you know, if we just think of hardware as temporal sequences of instructions, we're sort of, you know, not really taking advantages of all the inherent parallelism in the compute substrate, right? So that's sort of a difference. You know, people always ask me, like, why are you interested in sort of parallel computing? Is because chips are inherently parallel. You know, I mean, if you just throttle them down to a sequential thread of execution, you're sort of wasting most of the resources on the chip. And in fact, that's why microprocessors are so unbelievably inefficient, right? I mean, instead of using 1 billion transistors, or I don't even know, I think this latest Apple chip has 10 billion transistors, which are always executing all the time. You know, we just have this simple single thread of execution. Maybe we do a 32-bit add or some small number of them, which is just a tiny, tiny compute load for a chip like that. So anyway, so this is sort of something to keep in mind. You know, a lot of software people, they just get so enamored with this single thread of execution, but that's just not how hardware works. Okay, so we talked about streams. I want to tell you about another sort of cool idea, which is what's called Dataflow architectures, which is also a hot topic in hardware. It was a really hot topic. A lot of these were once really hot topics, and you know, are sort of now rebounding as people start get into more hardware. And Dataflow, as you might expect, is sort of a cool idea. It's sort of related to streams, but Dataflow is a little different. So Dataflow introduces some new operators. So so for example, well, so this is from a really great talk by Arvind, who many may know. He's a great researcher in computer architecture and programming languages at MIT, and he gave this nice little talk at the Oregon Programming Language Summer School in 2018, and this is from his slides. So I just stole his slides. I hope he doesn't mind. But he sort of said, you know, here's how Dataflow is sort of like what I said. When we have these sort of like streams, which are these like, you know, these things with these arrow things, or think of those as streams. Then we have these nodes, which are like compute elements. But Dataflow, so we have these primitive operators, which are sort of like the inverse I had, the map, not. You know, and you could have binary ones like add, right? So they, you know, and what's going to happen in Dataflow is we're going to have information flowing along these streams, and they get connected up. Okay, so this sort of shows you have some information here, you get one of these fork things, which just is a wire, and now the information gets duplicated and flows along both of the forks. Then if we had an adder, we got two inputs here, the blue and the yellow, and then we compute, when we get the two inputs, we compute the addition, which is the green circle. Then, but Dataflow has some additional things that weren't in the simple stream model, at least in the way I described it. So it has this thing called a switch, right? Which sort of says, you know, I have some token T, this red thing, and if it's true, this blue bubble will go down the true branch, and if it's false, it'll go down the false branch. So this is a little different, because now, in some sense, you know, there's no value getting forwarded along this branch. So normally, if we had streams, there'd always be values defined on every one of these things, but we didn't actually compute a value here. And then there's also this thing called merge. So you can think of this sort of maybe like merge sort, where what we do is we have two inputs here, sort of reverse of this one, coming in the T and the F slots. And then what we do is we decide which one to forward on the output line. So if it's true, we forward the blue one, and if it's false, we forward the yellow one. So this is a little bit different than the stream programming model. And so here's my implementation of it. Actually, let me go to that code. anyways, so this is the same as before. I changed it from stream to Dataflow. So now in a Dataflow architecture, each value in this is not necessarily mapped to a given time. So you can think of like each of these wires as information flowing along them, but it need not be that there's new information flowing on them at every time. So think of maybe them as just queues, if you like, right? So if I had two lists, and like if I wanted to implement that merge operator, I'd have two lists as inputs, and I would take one of the elements on one of those lists and put it on the other one. So that's what this thing here is showing, this merge thing. So what we do is we say merge false. So we have the merge takes 3 of these Dataflow lists, and it produces another one. The first one is the sort of toggle, and then we have X's and Y's. And if it's false, we grab the X, we return a list which is X, and then we continue the merge, and we've taken away the leading X on the list of X's. If it's true, we do it this way. So hopefully this program is clearer than my explanation. Then there's also some other functions that are very useful. T-gate is sort of a variation on it, where you forward the argument only if the value is true. Okay, so for example, you have T-gate of true, then you forward the X, and then you apply yourself recursively. If T-gate is false, you just throw away the X. So nothing gets output. And F-gate is sort of the reverse of that. And then there's another one called gate, which just sort of says, if there's some token at all in the input, doesn't matter whether it's true or false, then you forward the X and continue. So anyway, so these are just sort of functions that control the flow of data. So let me see. So those are just some functions. Yeah, they're all there. Okay, so here's an example in his talk, Arvind's talk. So we say we make this little circuit. And again, notice that there's cycles in this thing. So it's very common to have cycles in these things. So this is meant to be one of these T-gates. So O, which is the output of the T-gate, has I coming in, and then it has A acting as the toggle. So if A is true, okay, we forward something, we forward I to the output. Okay, if A is false, we don't. Then this simply says, as inputs flow in, this just says, whenever there's an input here, forward something through this gate. And then here we have our combinational function here. Okay, and anyway, so this is a circuit. It's very much like the toggle flip-flop, except but implemented in this way. Right here we have this thing going, cycling around here. This is just cycling around, and every time we go around, we toggle it. So it starts out as true. So he used T here for true, and then it goes, and then it gets nodded. So it's very similar to our program before. And by the way, this thing here, actually, Kahn and Dennis, if you know this history of this, they studied these networks like this in the early days, and they showed that these things actually will always lead to stable, unique solutions. I'm not going to go into that, but sort of interesting theoretical thing. So anyway, so the way you evaluate this thing is, say you have some inputs, I1, I2, I3, okay? Now what you just sort of do is you sort of have to iterate here. Remember, you have this mutual set of recursive equations. You have to iterate here to sort of grow this list. So it's a little bit like lazy evaluation. So first of all, you say, well, do I know the values of any of these things, O, A, or B? Well, I know the value of I, that's the input. Well, but I know the first value of B because it's this concatenated list, so it's T. So I say, okay, so I can compute T here. I can compute the first value of T. But once I know B, okay, then I can compute A. Okay. So then I can compute A, and then once I know A, remember I know A and I now, I can compute O. And so I get I1. And so there's some way of iterating here. So we say this set of equations has a unique fixed point. If you know about abstract interpretation, right, then this is actually sort of very similar to the algorithms we use in abstract interpretation. But that's just an aside. Don't worry about that. But it is actually interesting. I almost was going to spend 10 minutes talking about abstract interpretation of hardware. Sort of interesting subject in itself. But let's not go there. Okay. So anyways, so if I go to my program now, so what does this thing do? So here's the down program. Here's down, which is just what I just said in my language, not his, using my implementations of these standard functions. And there's also one called up, but let's ignore that for a second. Or I'm not going to show you that one. So I can say take for, remember, I'm building upon what I already built. Okay, so I get this alternating sequences of that, of false, true, false, true, false, true. If I take for, and then I say down of TFF. So TFF is false, true, false, true. I run down on that. You notice I get false, 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 false. So this down actually is a downsampler. It's throwing away every other element of the stream. So it keeps the 0th element, throws away the 1st element, keeps the 2nd element, throws away the 4th. So that's what that T-gate did, right? If the input to that T-gate is false, it just throws away the element. So this is what's very different about Dataflow than normal stream programming, is you can control the sizes of these lists. You can drop elements from the lists. Okay, you can merge lists. Okay, it's considerably more general programming model than simple stream hardware reactive programming. It's a very powerful computing model. And what that up did was sort of the reverse of down. Okay, what up does is what we call upsampling. It duplicates every element in the list. So the false went to false, false, the true went to true, true, false, false, true, true, false, false. So we've now in this model, we can sort of start doing things like signal processing where we upsample and downsample signals, not just compute on them. So that's sort of cool. And so things like Dataflow are, you know, if you want to implement a language which has things like filtering in it, or much more like what we might think as conventional list processing operations, Dataflow might seem a little more applicable than stream programming, simple stream programming. So anyway, this is sort of cool. Now, there's another sort of interesting thing about this. It's a little tricky to compile Dataflow programs to hardware because they're not simple streams. I mean, the stream model is actually very much motivated by combinational logic and sequential logic. The Dataflow model, that's not what the hardware is sort of intrinsically doing. So you'd have to build that on top of it. So let me just talk about one sort of way of doing that, and which is sort of cool, which you might call clock Dataflow. So what you could have, suppose you had a clock, tick, 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 tick. But now you had some data, okay? But you also create this other signal called valid, which if it's 0, that means the data here is sort of missing, not valid. It's just missing. There's no data there, okay? So for example, if we did that downsample, we had false, true coming in. If we downsampled it, we might just set the valid bits on all the trues to be 0. So now we would have, false, true, valid equals true, true, valid equals false, false, valid equals. So this is how you might actually implement something like that. Now, first of all, there's many ways of implementing Dataflow things, and this is not necessarily the most efficient, but you see this kind of thing done quite a bit in signal processing and stream processing, where you do this sort of clocked stream, if you like, where you have a data and a valid bit, and then and so on. So you sort of, every stream now has data and valid. So this is sort of interesting. Now, there's another concept here. There's just a lot of really cool things people have thought of for trying to describe hardware that I think, as a programming language person, you might like. So one question you could ask is, well, these data flow programs in general are very hard to analyze, right? Because they're patterns of the patterns of data they produce depend on the data, right? I mean, if you do that merge and you have a signal coming in, which could be some arbitrary data, you don't really know much about what's coming out, right? And or if you filter something, right, you don't know how many elements will be in the filtered list, because it could be an arbitrary computation of the filter. So it's hard to know much statically about these signals, those streams that are flowing through. Okay, but there's been a bunch of people, what they call, sort of do various variations of what's called synchronous data flow. Again, this is very old stuff. And one question you could ask is, there some way to statically analyze the pattern of valids? In other words, are there programs where the valids are sort of predetermined at compile time, if you like, and the data can just flow through? If you could statically determine the valids, okay, that would be quite nice. So there were a bunch of languages. I just want to point them out. They're almost all developed in the 80s. Lucid, Signal, Estral, Lester, okay, which are all sort of interesting to read about if you have some time. Not many people know about these languages. I mean, they all implement some kind of synchronous data flow like model, and they are quite different than a lot of programming languages you might have seen. They sort of start with this stream idea as a fundamental concept, and these operators like the Dennis and Kahn operators, and they embed those into programming languages. Now, there's another version of data flow which is much more popular. If you ask somebody what is synchronous data flow, I think I have all the terminology right here. There's another set of ideas popularized by Lee and Messerschmidt at Berkeley, which is something that's called synchronous data flow. Like at every tick, you consume a fixed number of inputs and you produce a fixed number of outputs. So you wait for, say, k inputs. Now, once you get the k inputs, you always produce, say, l outputs. And that's sort of that if you always have that property, okay, then you are statically analyzable, because you sort of have what they'll call like fixed firing rates. So that's actually, but the more general concept is, can you statically analyze the pattern of valids? So how am I doing on time here? Getting close to the end. Okay, so anyway, there's just one really other cool thing I want to tell you about. I just sort of was amazed when I discovered it. And that's this thing called the clock calculus. So suppose you wanted to write one of these programs and you wanted all these valids to be, statically analyzable and known in advance. Then what you could sort of do is, if you had two signals, let's say you're going to go A plus B, and A and B were these clocked signals with valids, then you would like to guarantee that every time an A arrived that was valid, there would also be a B there that was also valid. And that you never had an A that was valid arriving at the same time that you had a B that was not valid. Okay, right? You see the basic idea. Like I have these, I want to make these units, and I just want them to, I want them to always get valid values at exactly the same time. I mean, if you don't get valid values at exactly the same time, you might have to put some kind of like buffer in front of them, right? You might have to like store up the valid because the valid it needs to compute A plus B, the valid B might not have arrived yet. And so that would require buffers. And in general, buffers are what can make data flow really slow. So if you could prove that all the valids lined up properly, or you could transform your program into a version where all the valids lined up properly, then you could make it run really, really fast. So this is sort of a crazy idea, but there's a neat thing in here that you can read about if you want. There's a relationship between circuits and numbers. So this is just a fun fact, and then I'll end. Okay, so let's think about registers for a second. Let's imagine we think of our stream as sort of a number, right? We have a list. So think of each element of the list as a digit in the number. So think of each element in the list as a binary digit in the number. So if we had a list 0, 1, 1, right? Those 0, 1, 1s would be concatenated into a number. Then if you do the register that I mentioned, if you say register 0 and X, that means take the list of digits X and append a 0 to it. So if you imagine the first digit is the least significant digit, and then they were all increasing to more significant digits. If I just append a 0 in the least significant digit, that's equivalent to multiplying the number by 2x. And if I start it with a 1 instead of a 0, then I've multiplied the number by 2x, because I've shifted it. I've added the 1 or the 0 at the beginning, multiply it by 2x plus 1. And so you can actually think of, if you have a sequence of registers, these little circles means you're knotting various things, you can actually interpret the calculation as producing a number. And you can try to think about this for a while. Now, so actually what's this notation here I'm using is if I put a 0 in parentheses, that means I have an infinite list of zeros. So if I feed in an infinite list of zeros and I knot it and then knot it again, I get a 1. So this corresponds to 2x plus 1, followed by an infinite list of zeros. And then I can multiply it by 2x again, and that shifts it over. So the numbers are sort of getting pushed to the right here in this example, and so on. And if I knot something, I flip all the bits, and so on. So anyway, this is sort of not obvious, but sort of cool. But anyways, I'm sort of running out of time, but you can show that any self-contained synchronous circuit, self-contained, I mean it has no random inputs, it just is a circuit that's running by itself, okay, will produce an infinite periodic sequence. So eventually it has to repeat itself. And you can't make a circuit, you can't make a finite circuit in logic that eventually does not repeat. It can take a long time to repeat. If you ever looked at like pseudo-random number generators or things like that, they can take a long time to repeat. You could say, how to make a circuit that, has the longest possible, interval before it repeats. But in general, it will eventually repeat. So if you have a repeating number, you can sort of think of it as a rational number. Because if you remember, if you have any kind of rational number, will be written as some sort of leading start sequence followed by a repeating sequence. So anyways, this is sort of a cool fact. And, I'll just mention this. You can come look at my slides or come after. But there's actually a neat way of doing this, which is what's called leftist numbers or two-adic numbers. And the way this works is you form a repeating sequence, but instead of extending it off to the right like you think of for rational numbers, you extend it to the left. you extend it to the left. So you think of 1, so remember this is an integer 1, as 1 with an infinite sequence of zeros to the left. Now you think of -1 as sort of an infinite sequences of 1s to the left. And remember, this is an infinite sequence of 1s. So this starts looking like 2's complement. It's sort of like an infinite sequence of 1s going off to the right. And then you can use this technique for forming rational numbers, like -1/3, 1/3, and so on. And so you can transform any of these fractions into one of these repeating sequences, and you can also transfer these repeating sequences into fractions. So any circuit, in some sense, the cool thing about it is any sort of finite circuit, if you look at the stream of any kind of finite circuit, it's going to be represented just with a number, which is sort of an unbelievable thing. I mean, it could be a complicated number, but now you can say, well, I have this signal, which is a repeating signal, and there's a fraction, that represents it. And so that is really neat, because now suppose I have two numbers, I have two repeating sequences, I can convert them to the fraction and see if they're the same fraction. So I have two clock signals going into that adder, and I can say, well, are those two numbers the same? And I can solve this problem to say that the repeating sequence of valids on these two signals is the same. So that's, I don't have time to really explain all the details of this. It's just a fun little non-obvious thing, but I thought you might be amused by it. So I'm going to skip over this last little bit on this. So what you can actually do then is you can sort of form expressions involving these p-adic numbers or two-adic numbers, and you can build circuits where you have different computations like and not and add on these p-adic numbers, and so you can form functions on these valid signals, and you can actually compute on them in advance and statically analyze the program. So anyways, I'm just going to mention this. So this lets us sort of take certain kinds of data flow programs, these static data flow or synchronous data flow programs, and compile them very, very efficiently into hardware. Okay, so two final thoughts. So first of all, I do want to point out the relationship of what I've been talking about functional reactive programming. So reactive programming is becoming a pretty big thing, I think, and there's lots of debates about it. I first learned the functional reactive programming from Conno Elliott, and of course, he built the system with Paul Hudak. It's actually, so some people call stream programming reactive programming. So if you look at the literature in hardware, they often call stream programming reactive programming. And furthermore, if you even look in embedded computing or real-time computing, you very often see the term reactive programming to mean essentially what I was calling stream programming of various types. I do want to just sort of mention maybe some similarities between functional reactive programming and what I've been talking about in hardware. So one of the features I think Conno would say is true of his idea of functional reactive programming is that time is not discrete, that you have continuous time, right? Time is like a real number, floating point number, but you still may have these events which are discrete things. For example, if you have a user interface and you click on the mouse, that's an event, that's a discrete thing. But you're trying to define the animation on the screen as a function of all this stuff. And so the time is continuous. And one of the arguments for this, I think he makes very eloquently, is that one is you can be sort of temporally resolution independent, right? You can stretch programs out or shrink them, compress them. You can transform time if you want to rescale them. And you can do things like integration and differentiation in some sense. I mean, you could argue equivalent things in discrete things. But there's advantages to doing this in continuous time. Now, if you think of hardware, I actually have one of these behind me. This is an analog computer. It's a circuit with a bunch of operators where everything is being done in continuous time. And I have patch panels that wire up all these circuit elements. This is called a COMDYNA GP6, which is an old analog computer. And if you've ever used like SPICE, I mean, in some sense, it's very similar to the circuits I was talking about with ands and nots and so on. But you have things like resistors, and you have these little circuits are just, nodes that are all wired up, and they can have cycles. So in SPICE, if you've ever used SPICE, you could, wire up some resistors and capacitors and make an oscillator or whatever. But if you've ever tried to do analog programming, it's a little tricky actually. And the function space is much more complicated. I mean, you have arbitrary, in some sense, you can define, any function you want, and now you can do, and you can define very crazy functions. And if you've ever used SPICE, it can actually be hard to get it to converge. So if you run different versions of SPICE, you have to have these integrators, these ODE integrators that integrate it out and make it work. And I mean, it's pretty robust, but it's much more complicated to have circuits. In some sense, analog circuits are much harder to design and reason about than discrete circuits with discrete time. And actually, if you ever read Claude Shannon's thesis, he was working for Vannevar Bush, who was a big analog computing person. And Claude Shannon actually proposed using digital computation, using Boolean algebra, as a way of simplifying computation, because analog computation was so hard to analyze. So anyways, it's just something to think about. I actually think for a lot of reactive programming, the really simple model of stream programming in hardware is actually pretty nice. I use it in some, I do graphics, I use it in some little game engines I've built and so on. I just keep it really simple. I think of each frame, okay, as being the clock. And when the clock ticks, I update the screen, and the screen is a simple function of the state. And then I update the state, sort of like that Moore machine. And it just makes it really easy to analyze things. And it's not like it does everything, but for a lot of games I've written, it works really well. So anyways, we can talk about that afterwards if you want. But so anyways, I'm actually pretty excited about hardware. I haven't talked about my research. I've been trying to make it easier to build hardware. It's actually a really exciting time in hardware. I do think even if you're, I would encourage you to maybe get involved in some hardware things. One, of course, all of us doing hardware design could use help from people that know about programming languages and advanced software techniques. But I think even if you are a software person, I think it's really useful to have this hardware perspective. I mean, one is, computers really are spatial temporal things. Okay, it's important to know what is efficient and what is not. A lot of people really have strange notions about what efficiency is. And if you know a little bit about hardware, you'll have a much better idea about efficiency. For example, all the energy goes into communication, not computation, and so on. Also, I mean, there's mathematics, right? A lot of programming languages is based on very cool mathematics like category theory and great stuff. But computers really are physical devices. So you have to sort of have mathematics that's grounded in physics. And we could argue about that, but if you're going to really build real computers, and I tend to build real computers, the physics is going to be involved there somewhere. And it doesn't mean we can't abstract them in all sorts of interesting ways, but we still have to be aware that they are real devices. In my research, we're really just taking this really simple idea that hardware design is more like writing software. It sort of seems fairly obvious, I mean, computers are computational devices. Hardware is just a program that's embedded in silicon. And so it's clearly a program. It's not like a general program. I mean, it has constraints, but a lot of the techniques we use for defining abstractions and composing software and scaling it up and so on, testing, all these things, I tend to think the software community is way ahead of the hardware community. And so, I think it's a really great opportunity for us to really revolutionize hardware design. And I think it's actually going to be a very fun period in hardware design, because for the first time, I think you're going to start seeing people build a lot of different hardware devices. And we're going to start seeing these devices sort of invade our world, and that's going to be really quite cool. So with that, I'll end. I think I'm out of time, right? So thank you.
Yeah, so
I'm happy to take some questions.
We're a bit over time, but since it was the last session, I allowed it. So maybe we have some time for some quick questions. I'll look at the Q&A session.
Yeah, I'll go to the Q&A session afterwards. Sorry I ran late.
Yeah, that's so I was totally blown away. It's sort of like a modern age hackman, really. So it's great stuff. We can take one question from Stephen Proctor. He says, from thinking about hardware from a software-based design perspective, what assumptions, if any, around current hardware design should be challenged on the hardware design side, and how might those look?
I'm not sure I caught all the subtlety. What should we challenge in hardware design?
Yeah, I think you can see the question if you look at the Q&A session tab to the right on your screen. So Stephen has raised.
It must have scrolled off. I can
over to him so he can. So Stephen, you're welcome.
Oh yeah, why don't you just ask me in person? That would be awesome.
Yeah.
So you're looking at the hardware design from a software perspective. Is there anything that, as you think about it from writing it in software, that would challenge any current or long-standing things about how we think about hardware based off what you're seeing and you're bringing from a software perspective?
Well, the biggest thing I've noticed that the hardware guys have not been able to do, maybe a slight variation from your question. It's not so much about the hardware they're building, but the way they build it, is they really do not reuse hardware very much. If you think of software, I mean, to me, this is the number one surprise to me when working with hardware teams. I mean, you would think that they would have huge libraries of reusable components, huge libraries like we have in software, right? Huge libraries, that they would have robust ecosystem of programming models that would allow them to combine libraries together and have different kinds of implementations and so on. And that is not the case. So not that there's no open source hardware and no libraries at all, but there's just, even the simplest things have not been, they don't have the way I sometimes describe it to people is they do not even have the equivalent of libc. You know what I mean? So they don't have these standard libraries at the low level, and I think that has limited them more than they think. Now there's reasons they don't have those. We can talk about it, or at least they have reasons they tell me they don't have those. But I think that's where, that will be the biggest breakthrough, is if we can get them to start building libraries of reusable components.